We're continuing our study of sets by talking about some set operations. The first of those is a union of two sets. The union of sets A and B, as indicated here, A union B, it's the set of elements that are in either A or B, or they could be in both. So the union of two sets is just dumping all the elements together into one big set. You can visualize this graphically if you think of each set as being represented by a circle. The shaded area is the union of the two sets. Everything in either or both of the sets is in the union. For example, suppose I ask you to find the union of the set A with the set B here. You just need to dump all the elements together. So if I just toss all the elements of A and all the elements of B into one big set, that is the union. However, when writing sets, we don't duplicate an element. So if there are any duplicate elements, we eliminate those duplicates and we have the union. And you'll notice here that there's a 3 in both A and B. We have to eliminate one of those. There's also a 6 in both and an 8 in both. If you eliminate those 3 duplicates, you get the union of those two sets. Pretty simple concept. It's mainly just a matter of being careful. It's also not necessary, but quite often if they're letters of the alphabet, you might want to just put them in alphabetical order. If they're numbers, you might want to put them in numerical order. It doesn't change the fact that it's the same set, but you might want to put things in this case, numerical order. And that's what I've done here. Now, as I said, the graphical illustrations are sometimes useful. If you go back to the circle idea, you can think about dumping the elements of A into the circle A and the elements of B into the circle B, and you'll notice that the 3 and the 6 and the 8 that were duplicated in both sets go in the overlapping region that's a part of both. That's a really nice visualization of the union of two sets. Talked about union. The other concept that's very common with set operations is the idea of intersection. The intersection of sets A and B, the union symbol is essentially turned upside down for intersection. The intersection of sets A and B is the set of elements that are in both A and B. With union, you just dump the elements in. It doesn't matter. They can be in either or both. But for intersection, you're only interested in the ones that are in both. If you look at the picture, the graphical representation that I put up a minute ago, the crosshatched region is the intersection. It's the overlap that visually represents the intersection of those two sets. Again, if you went back to an example that we did earlier, you can see that if you're looking for intersection, you're only interested in the elements that are in common to both. And there's a 3 and a 6 and an 8 in both. And those 3 elements make up the intersection. So for intersection, you're looking for the overlapping elements. And again, going back to the visualization, those overlapping elements go into that crosshatched region that I showed earlier, and that crosshatched region represents the solution set for the intersection. Talked about union, talked about intersection. The next set operation is called the complement. By definition, if A is any subset of the universal set U, the complement of A, and it's denoted with this accent symbol, consists of all elements in the universal set that are not in A. So for example, if I gave you a universal set consisting of the counting numbers from 1 to 7 inclusive, and I said the set A consisted of the elements 1, 3, 5, and 7, the complement of A are the things that are not in A but are in the universal set. So I'll eliminate anything from the universal set that is in A, and what's left will be in the complement. So I notice that 1 and 3 and 5 and 7 are in A, so they get eliminated. That means that the complement consists of the elements of the universal set that did not get eliminated. And that's the idea of complementation. They're all the elements in the universal set that were not in the set you were complementing. At this point, there is something I'd like to point out. If you go back and look at the set A and the set that you just found, which is the complement of A, if you take the union of A and A complement, notice what happens. If you take A, which is here, and A complement, which is this, and you do the union of those two sets, you end up with the universal set back. And that's always true. So just keep in mind that that is a general result, not just specific to this particular problem. If A is any subset of U, then A union A complement is always equal to the universal set for any A. You can also talk about the difference of two sets. I'm going to define the difference as B minus A. The difference of set B and A, which I'll denote B minus A, is a set consisting of every element of B that is not in A. Let's look at that through an example. Suppose the set B is a set consisting of 1, 4, 7, 8, and 11, and A is the set consisting of 2, 4, 6, and 8. B minus A is defined to be every element of B that's not in A. So before you put something in B minus A from B, you always start with B. The set on the left is the one you draw from. But you only put it in the difference if it's not in A. So if you're looking one at a time at set B, you're always starting with the set that appears on the left. 1 goes in because it's not in A. 4 is in A, so it doesn't go into the difference. 7 is not in A, so it does go into the difference. 8 is in A, so it does not go into the difference. And 11 is not in A, so it goes in to the difference. So the difference between B and A, represented as B minus A, all the things that are in B, so you're pulling from here, from B, but you only take the things that are not in A. And if you look across here, the only things that are not in A that are in B are 1, 7, and 11. And that's what goes into the difference. Now, just like regular subtraction, the order matters. If you said A minus B, you'd reverse the roles. You'd be looking at A, and you'd be pulling elements from A, only if they're not in B. And that's the idea of the difference between two sets. If it helps to think about this visually, you can go back to the visual aid that I gave earlier and think of it this way. You're basically working with set B. That's why it's mostly colored in. You're basically working with set B, but you take out the things that were in A, and that's why the overlapping circle A limits B. So the things that were in A and B, if you think about this, the things that were in both, in this area right here, got eliminated from the difference. So it's like putting down the set B and then putting A over the top of it, and what didn't get covered up in B is in the difference. And again, if you had a reversal and you put the A where the B was and B where the A was, then the A would become the base circle and would get covered up by part of B. And that's a visual way of looking at the difference. Another interesting thing that we could verify if we wanted to, is that the difference B minus A is equivalent to an operation with union. B minus A is the same thing, and you could show this if you wanted to, as B union the complement of A. I'm not going to derive that here, but I could. And if you reversed it and said A minus B, then that would be equivalent to A union B complement. We also have De Morgan's laws for sets. De Morgan's laws for sets says if A and B are sets, then the complement of the union of A and B is the same thing as A complement intersected with B complement. And the complement of the intersection of A and B is the same thing as A complement union B complement. And you can see how this works. The complement gets distributed to both positions, and the union changes to an intersection. Same thing here. The complement gets distributed to both sets, and the intersection changes to union. So De Morgan's laws for sets is really easy to remember. The complement symbol distributes, and the union or intersection gets flipped. Let's use it in a simple example. What if I ask you to show that the complement of A union B is in fact equal to A complement intersected with B complement for two particular examples? A is the set containing 1, 2, 3, 4, 5, and B is the set containing 2, 4, 6, 8. Notice anytime I'm talking about complements, I have to have a universal set. So in this particular problem, universal set will be the counting numbers 1 through 10 inclusive. You can't take a complement without having a universal set. So let's show that this first piece of De Morgan's laws for sets is true for these particular values. First of all, let's take the left-hand side. That's the complement of the union. Well, A is the set containing 1, 2, 3, 4, 5. B is the set containing 2, 4, 6, 8. I want to union them together, and then at the end I will take the complement. But when I union 1, 2, 3, 4, 5 with 2, 4, 6, 8, remember you just toss all the elements in and remove duplicates. You'll end up with 1, 2, 3, 4, 5, 6, and 8. Notice there's no 7 anywhere. Now I want to take the complement of that set. Remember, the complement are the elements that are in the universal set but are not in the set I'm complementing. So you look through, and anything that's in this set that I'm complementing does not go into the final result. So if I look at it, there is a 1 here, so it doesn't go in. There is a 2 here, it doesn't go in. There is a 3 here. There is a 4 in there. There is a 5 in there. There is a 6 in there. But there is no 7, so 7 goes in. There's an 8 in there, but there is no 9 in here, so it goes in, and there's also no 10, so it goes in. So I'm taking the things that are in the universal set but are not in the set I'm complementing. So what I've shown is that the complement of A union B is the set consisting of the elements 7, 9, and 10. So now I have figured out what the left-hand side is. I'm trying to show that that's the same as the right-hand side. So now I need to work with the right-hand side and show that it comes out exactly the same. So let's do that. The right-hand side is A complement intersected with B complement. Well, A complement are the things that are in the universal set that are not in A. Well, look at that. If you look at the universal set, 1, 2, 3, 4, and 5 from the universal set are in A, so what's left over is 6, 7, 8, 9, 10. If you look at B complement, there's no 1 in B, so 1 goes into the complement. There is a 2. There is not a 3 in here, so 3 goes in. There is a 4, so you don't put a 4 in. There is no 5, though, so you put 5 in. There's a 6, so you don't put 6 in. There is no 7, so you put 7 in. There is an 8, so that does not go in. And then looking here at the end, you have a 9, and a 10, so those go in. So this set is A complement, and this set is B complement, and now I want to intersect them. Remember, the intersection are the elements in common. So if you look, there's a 7 in both, a 9 in both, and a 10 in both. So A complement intersect B complement is the set consisting of 7, 9, and 10. But notice, that's the same thing. So in fact, the left-hand side here is equal to the right-hand side here. So what I've shown is, for this particular instance, I have not proven it in general, but for in this particular instance, A union B complemented is equal to A complement intersect B complement. It's just sort of an exercise to get you thinking about those De Morgan's laws for sets. They're very easy to remember, but practice helps. And this time we're going to use the second of De Morgan's laws for sets and do the same thing we did before. I'm going to use the same universal set in A and B just sort of for consistency. But this time I want to start with the left-hand side of the second one of De Morgan's laws for sets, and that is A intersect B complemented. So the first thing I want to do is find A intersect B. Remember, A consists of the elements 1, 2, 3, 4, 5. B consists of the elements 2, 4, 6, 8. And if I intersect those sets, I just get the things in common, which would be the 2, the 4, and that's it. But don't forget, I still have to complement that. And the complement of a set is everything in the universal set that's not in the set you're complementing. So I have out of the universal set, there's a 4 even though it's not showing up with the dot dot dots. There's a 2 in this set that has to be eliminated, and of course the 4 has to be eliminated. So everything else in the universal set, the 1, the 3, and then 5, 6, 7, 8, 9, 10 would be in the complement. Notice I've just taken out the 2 and the 4. Everything else in the universal set shows up. So what I've done now is shown that the complement of A intersect B, which is the left-hand side, comes out to be the set containing 1, 3, 5, 7, 8, 9, and 10. Now I want to take the right-hand side and do the similar thing. Now, A complement is everything in the universal set that's not in A. So if I go back and look at A, I notice there is a 1, 2, 3. In fact, there's a 1, 2, 3, 4, 5. So everything from beyond 5 goes into the complement, which would be 6, 7, 8, 9, 10. B complement is everything in the universal set that's not in B. So now I want to take the 2, 4, 6, 8 out of the universal set. So the 2 and the 4 and the 6 and the 8 come out. And when you get rid of those, you're left with 1, 3, 5, 7, 9, and 10. So I've done A complement here, I've done B complement here. Now I want to take the union. Remember, the union just throws everything into the pot. So you put all of those elements into one set and get rid of any duplications. And that gives you the set containing 1, 3, 5, 6, 7, 8, 9, 10. And notice that it is equal to what we did earlier. So I've shown that the intersection of A and B complemented is the same thing as A complement union B complement for this particular problem. Again, this is just practice getting you used to using these things. We also have something called the union rule for sets. The union rule for sets says if A and B are sets, then the number of elements in the union of A and B is the same as counting the number of elements in A and the number of elements in B and adding them together, and then subtracting off the number of elements in the intersection of the two sets. Let's look at that graphically. If I go back to my circle idea of representing each set by a circle, then what I'm saying is, and I will use particular numbers just to make it easier to see. Suppose set A has 7 elements, but they're distributed so that 5 of them are in A but not in B, and the other 2, they're still inside of A, but they're also in B. So A does have 7 elements, but they're distributed as so. B, similarly, it only has 6 elements, but 2 of them are shared with set A, the other 4 are not. Notice there are still 6 elements in B, and there are still 7 elements in A. They're just sharing 2. So this is the setup. Now let's calculate the left-hand side of the union rule for sets. So we want to know how many elements are in the union of A and B. Remember, when you take the union of 2 sets, you just throw everything together. So there are a total of 5 plus 2 plus 4, which will be 11 elements. So the number of elements in the union of A and B would be 11. So I've done the left-hand side. Now I want to do the right-hand side. The right-hand side has 3 pieces, so I'll have to do 3 counts. First, I want to do the number of elements in set A. Well, that's easy. There were 7, and you can look here and see that there's 7. Then I want to do the number of elements in set B, and again, you're given there were 6, but you can also look at the graph and see that there's 6. And then the overlapping elements are in the intersection, so there are 2 that are shared. So what you can see is that when you counted 7 and then you counted 6, you ended up counting the overlapping elements twice. That's why you have to subtract off one of the counts. You counted 2 twice, you have to get rid of one of those 2s. And that's why the union rule for sets is what it is. And that comes out to be 11. So what I've shown is you get 11 in either case. So the number of elements in the union is the number of elements in each set minus the number of elements in the overlap, because you've counted those twice. So those 2 quantities are in fact equal. And again, I haven't verified it in general. I'm just showing you with particular numbers to make it more concrete. Now let's take an example where the union rule for sets might actually be useful. This problem says if the number of elements in set A is 75, and the number of elements in the union of the 2 sets is 150, and the number of elements in the intersection of the 2 sets is 25, how many elements are there in set B? You could actually try to draw this out graphically with the circles, but if you know the union rule for sets, this is actually the easiest way to do it. Just write it down and plug in your knowns and solve for whatever is unknown. So I know the number of elements in the union is 150, so I just plug that in. I know the number of elements in set A is 75, so I just plug that in. I know that the number of elements in set B is what I'm looking for, so I might just call that X. And finally, I know the number of elements in the intersection of A and B is 25, so I plug that in. Now I've got a simple equation to solve. On the right, 75 minus 25, of course, gives 50. And then to solve for X, I can subtract 50 from both sides and get X equal 100. So that tells me that the number of elements in set B was 100. And that's an application of the union rule for sets.